And it's my pleasure, my great pleasure, to introduce you to the second keynote speaker of COLATEC conference in Barcelona 2024. And we are privileged to listen today to Professor, our colleague, friend, Ulrich Hoppe. He's currently Emeritus Professor at the University of Duisburg-Essen in Germany. His topic for today is focused on the evolution and prospects of networked analysis in collaboration within digital communities. And the topic really promises insightful reflections on a field to which he has significantly contributed. His kind of retirement is challenging to accept for our community, as we deeply value his ongoing influence and insights. I met him when I was a Ph.D. student in the context of an European network, Kaleidoscope. We all remember very well that network. And an initiative related to CACL. That was in 2005. And if my memory doesn't fail, it was also one of the first time I also met him, and in that period, it was at CREW 2006 in Valladolid, Medina del Campo. I don't know, you didn't attend that one? But yeah, some people here, maybe Gustavo and others. It was already, the CREW was the initial times of COLATEC. And I was serving there as a volunteer. I was not imagining at that time that I was going to be a local host years later. But his work, Ulrich Hoppe work, and the work of his research group that he founded in 1995 has been very influential to me, particularly in my first period as a researcher in training, specifically in the domain of distributed collaborative learning environments, computational representation and orchestration. And later, also influenced me his work on intelligence support in educational systems and analytics, including network analytics. He has been very active in European projects, and myself, but also my team, the Thai research group, feel very lucky of having had the opportunity to visit his team in Duisburg and share some of his and our latest projects. For example, CS-Track on web analytics and citizen science, Courage on AI, artificial intelligence companions, to educate about social media risk. Last but not least, he has been very active in serving to the community by participating in societies and committees, often in roles that are not immediately visible, driving the advancement of the communities, including, but not only COLATEC, towards greater relevance, scientific rigor, and very importantly for many of us, showing the relevance of computer science contributions in interdisciplinary domains that connect with the learning sciences. Ulrich, we still want you to influence us. Thank you very much for being here. Please join me in welcoming Professor Ulrich Hoppe in his keynote today.
Thank you very much, Davinia, for the warm, insightful, and very generous words that you have found. I really appreciate that. I've always appreciated working with you, and I have also appreciated being a member of the COLATEC and former, do you say CREWIG or CREWG? There are very different pronunciations of this community. So this is an important part of my professional profile, I would say, and I'm very happy to have been invited at this point, a bit looking back, of course, to this work. And the topic of today, network analysis approaches in research on collaboration in digital communities, evolution and prospects, has been very important to me at least over the last 15 years, you will see a bit of that, how it relates. I hope I can get that through to you, what it means to me and what it may mean for the future and for our understanding of the field. So, yeah, first a preview. We have seen a video yesterday. I think this mountain was not in the video, but you will know it. Many of you, the locals, should know it. It's the Pedra Forca in the pre-Pyrenees, I think you would say, or is it already Pyrenees? Oh, yeah, at least it's a very nice mountain. So let's descend from the mountain. Part 1 will be SNA, social network analysis, and its uptake in computer-supported collaborative work as one part of our topic field. Background, some general background, and then some example applications. Part 2 will be SNA applications in CSCW, where I will particularly focus on the analysis of productive online communities. And also then, at the end of that part, I would reflect on the classical methods of network analysis. And then the last part is a bit a window to the future and discusses the challenges that we are currently facing when we try to combine network analysis with new AI, with deep learning. This happens. And so we have to look at using graph embeddings, the networks in the form of graph embeddings, and I will do that for a specific purpose, and will then finally reflect on this part, and then I hope we have a lively discussion. Okay, social network analysis and its uptake in CSCL. You see, I put social in parentheses. As you will see, the network analysis techniques are not limited to social networks, and it's the same techniques, irrespective of the nodes being humans, actors, or concepts, or, for instance, artifacts. This is all possible. So, but to start from the beginning, so we have networks which are represented as graphs in the mathematical sense. Graphs consist of nodes and edges. In our case, the nodes typically are human agents, but also possibly mediating objects, nodes, sketches, articles, yeah, other types of artifacts. The humans may be viewed as learners, as co-workers. The edges may be of the type interacts with, shares with, or depends on different types of relations. Sometimes you also have multiple relations in such a model. When you look at the networks, there are different types of networks. We can have undirected or simple graphs. Simple means that they do not even have loops, whereas an undirected graph could have a loop. We have directed graphs, graphs with edge weights, so-called multigraphs that goes a bit beyond. These allow for establishing multiple edges between the same pair of nodes. Sometimes you want that. And we have very important bi- or multipartite graphs. We also call them multimodal networks in the network perspective, which allow to integrate different types of nodes and restrict the connections only to nodes of different types. A very interesting representation. So we are talking about such representations, and one first advice, and in my talk I will often try to give you recommendations how to use. Go for the richer representations first, because mathematically it's usually very easy to generate the simpler representations from the richer ones. Once you start with the simple ones, you will never get the information back. Yeah, okay. So then there are typical methods of analysis, and as you see here, I will not reveal that now at this point, but you can be assured at a later point in the presentation, I will give you the full table with some comments where the red question marks are now. So we have centrality measures that we use to determine influence or importance in a network. We have reciprocity to model balancedness of relationships in directed graphs. We have density. I would always recommend to combine it with average degree because they have different properties, but are in a way also similar. We have community detection methods, and we will have a look at that. Now, SNA can be viewed historically as an interdisciplinary project, which started as early as the 1930s with Moreno's sociograms, social psychology background. Haider in the 1950s, he was interested in balanced interpersonal relations, social psychology again, which led to signed graphs that were taken up in mathematics by Frank Harari. Then we have, in the 70s, Granovetter, sociology. He coined this notion, the strength of weak ties, related also to what we call structural holes in networks. Then we have Laszlo Barabasi, the first physicist coming in here, physics background. He elaborated on the notion, already existing notion, of scale-free networks. Then we have the first computer scientist, John Kleinberg, hubs and authorities like an alternative to Google PageRank that was already existing at the same time. Barry Wellman, sociology again, notion of social capital related to network models. And Duncan Watts, you may have heard 6 degrees of separation. So if you want to connect to anybody in the world, how many hops would you need? So this is just a few, but a few quite prominent ones. This dates 15 years back, and that's very personal. These are my notes. These were the notes on the chalkboard. Still had a chalkboard in my office, where we planned a course on network analysis that was then delivered to different master programs. I was, taken up quite positively. I had usually 50 plus participants in this master course over the following years up to my retirement in 2020. So you see here we have collected the important parts, graph theory in the beginning, a very important part, exactly 15 years back that we did that. Okay, now we move to CSCL as the first application field. And this will be based on a paper that we presented at the CSCL conference in 2017. The main author, Mariel Dado, originally from Philippines. She was a scholar in our Ph.D. program on user-centered social media at that point in time. And she based the analysis on a sample of 90 papers from a CSCL context, titles and abstracts as data sources. She used coding techniques, and then she used what we call network analysis, NTA, to extract concepts from these papers. These were transformed into graphs onto which we applied then what is called bipartite modularity maximization. You will see what that brought forth. I will not explain the details of that. First of all, here you see different concepts that were identified, like starting with degree centrality in general, density, etc. And here you see the frequency of these concepts in the corpus. Here you see these concepts classified. The light blue ones are centrality-related concepts. So you see they are clearly dominating. Then we have global network properties, quite less, but still more frequent than others. Like this includes density, centralization. Centralization has to do with centralities, but it's a global network property, whereas centrality is a node attribute usually. So then we have subcommunities, subcommunity detection, and some other. And you see this is more or less the frequency of occurrence of these concepts in this corpus. Now, we used a technique, a network analysis technique, which is a bit more sophisticated. It is based on bipartite graphs. In this case, the two entity types are CSCL concepts and SNA concepts. And now we have looked for interlinking between these different types of concepts. You will see in the CSCL concept clouds, there are also different types of nodes. The squares are learning settings. The circles are there are activities, and the stars are methods of analysis. So, but this is not so important for us here. Let's look at the global picture. And now you can first try to identify, so what can we say about these components? Each component is characterized by being similarly and quite densely connected to other components. And here, in the bipartite sense, we do only look at connections between CSCL and SNA, not within. And now, first we can characterize these components. CSCL1, when you look, maybe you can read some of the terms. That's the typical knowledge building approach in CSCL. Like Junoshima in Japan, for instance. The second CSCL component or cluster you can characterize as general classroom, or at that time also MOOC studies. And the third one has specificities that indicate that this is very much in the sense of interaction analysis. Davinia mentioned the Kaleidoscope project, the European one. That was the target concept, or the core concept was interaction analysis. It later moved, a lot of that moved to learning analytics meanwhile, but the earlier activity, research activity, was indeed interaction analysis. Now the SNA components or clusters, one is clearly around centralities. SNA2 is about global graph properties, also cliques as a first notion of subcommunities. And the third one is about subcommunities, reciprocity, also communication appearing, whatever that means. And now, of course, the interrelations are interesting. And what you see is that SNA1, centralities, that's covered in all the different versions of CSCL. But only CSCL3 has strong relations to all three SNA types. It means that interaction analysis was the field that say, most intensively used SNA techniques. And this continues in learning analytics, as I said. Now, not a surprise, but interesting to see it here in this way. Okay, here is a bit more details. You see the most frequent interconnections. Always to do with interaction, with interaction patterns, group work as an activity, etc. We could also identify from the other end the concepts that were most distant to SNA. So if you find in a piece of research literature notions of design process, cognitive style, cognitive presence, meta-discourse, all very important and interesting topics, but they are not so much related with network analysis. We have this frequent mention of interaction patterns. We saw in our analyses, we found possible misconceptions about the use of density. I will come back to that because that reoccurs. Yeah, let me make a short remark on centralities, and that comes from a recent journal review job that I had. Of course, I will not disclose anything here, and you will not be able to determine who brought this to the journal, and I think it was also finally accepted. It is research work in a CSCL context with small group interactions, 3 to 5 people in a group, and the authors used eigenvector centrality as a centrality measure for these groups in undirected graphs. Eigenvector centrality is supposedly a quite sophisticated, or the most sophisticated of these centralities, you can argue. In a way, it's a refinement of the simplest centrality measure, that's degree. It's just the number of connections that a node has is the degree. But if you do not just count the neighbors one by one, but you count them again by their weight, So if you kind of propagate such weights and use them in the counting, then you come to eigenvector centrality. There are different, the eigenvector wording comes from linear algebra because there are certain methods from linear algebra that you can use to determine that. So it sounds sophisticated. Is it a good choice? As you may imagine, it's not a good choice in my opinion. Why? So here you have a standard example network that is often used when you talk about centralities in textbooks. It's a so-called kite graph. You see the names of people, they're interconnected. Undirected network in this case. And you can calculate, I did that here using NumPy and network X, Python, to calculate the different classical centralities. And this is what you get, and I have turned them into ranks. Now I have a ranking of the nodes, of the names, by their centralities. And let me see if I get the mouse here, otherwise I will try this one. Anyway, I can. You will see, for instance, that the degree rank, the highest is clearly Diane. If you look at the betweenness rank, interestingly, that's Heather. Heather only has a degree of 3, but she's a very important bridge between, say, the tail of this kite and the rest. So she's number 1 in betweenness rank, and closeness number 1 are Edward and Fred, both. If you look at degree and eigenvector centrality, it gives the same rank, no difference. For such small networks, very unlikely that you will find a difference between degree, simple degree, and eigenvector. Now, I made up an example here, very simple example. You see 4 nodes, 4 participants. Participant 3 has an overall degree of 4. The others have degrees of 2. If you just use normal degree measures, and if you used eigenvector, it would not be different. But if you use a directed graph, the picture changes quite interestingly. Then you have, for instance, 3 has 2 incoming, 2 outgoing. We call that in degree, out degree. 4 has 1 and 1. 2 has 2 in, no out, and 1 has no in and 2 out. So these are completely different profiles. If you now ask which of the 2 nodes are the most similar ones, you would probably, at least I would answer, it's 3 and 4, because they are balanced in their in and out relationships. All this you will not find if you use eigenvector on undirected graphs. And then you could say, why don't we use directed graphs and eigenvector centrality? That can be a bit problematic. You have to know that. I give you here the citation from Stock Exchange, but I will not follow up on that. Okay. As you have already seen from our analysis of the SNA concepts in CSCL, the nodes are not necessarily the people, but the nodes can be concepts, artifacts. Here, clearly they were concepts, and we used for the concept extraction and network generation, we used this technique of network text analysis by Kathleen Carley, Jana Diesner. This technique is based on running a sliding window over your text source, and whenever in one of these windows 2 concepts co-occur, you will establish a link. No directionality in the standard case. This is very similar for a newer technique, which has been used a lot in our field recently and also in learning analytics. It's called epistemic network analysis, ENA, by David Schaefer. The difference is that AutoMap and NTA, they work with quite open, say, code, open basis of terms and concepts that you can define, can be quite numerous, whereas ENA works with a smaller number of predefined codes, as you would do in qualitative ethnographic studies, for instance. This is really an inspiration for that technique. Also uses a sliding window approach and then projects the findings into a 2- or 3-dimensional space using dimensionality reduction techniques. And it's quite suggestive to interpret these diagrams, as you can see here. And if you have different versions using the same codes, you can compare the diagrams. You can also calculate difference networks, so to see the differences. That's quite handy for human interpretation, but there's a lot of mathematical apparatus behind. We should be aware of that. This is from, in first place from Davinia's work. It's based on work that they did here on teacher orchestration load. And there was a PhD student, Ishari Amarasinghe, here in the group. She came to our lab for a brief stay, and we used ENA on data that came from Davinia's, the work in Davinia's group here on teacher orchestration. And there were 3 conditions in this experiment. There was a condition in which the teachers, when orchestrating their classes, had no specific technology support. There was a mirroring condition, which was supporting self-monitoring. And the 3rd condition was also provided guidance, say, action recommendations. And here you can see the different profiles that these conditions generate when you look at the coded teacher activities. So the coded teacher activities, always difficult to get the mouse. Yeah. Let me try to do it just in words. Is it switched off? No. So, for instance, when you look at the condition C, there is a code check responses tab and announcement to class. That has a strong connection. That's here. Yeah. This is not so strong. Thank you. This is not so strong in condition B, and it's not existing in the A condition because there you cannot check responses tabs there because they are not there. So, did you get it? Or? Oh, it's there. Okay. So this let's just doesn't like me. Let's just take this difference, but you see how the ENA diagrams give you the different profiles. In this case, of teacher activity. Okay, this is CSCL so far, and in its relation to network analysis. I now move to CSCW as another important ingredient. Oh, thank you very much. And here, I will not cover the whole field of applications, but will focus on what I personally like to call productive online communities. You could call them POCs. So digitally connected virtual communities with purposeful activities, output-oriented activities, with products that are available in virtual or possibly also physical space. We know the standard examples, Wikipedia authoring. You may consider Fab Labs with online participation that may, for instance, generate 3D printed objects or something like that. Open source software development, online citizen science are all examples of this. And this is different. It's not a judgment. It's just a distinction from socializing communities, Facebook, TikTok, or whatsoever, but also from peer helping communities, like in the medical area. You have forums in which just people help each other how to deal with certain challenges, medical, psychologically, or whatsoever. They are not output-oriented typically. But they are, of course, extremely helpful. This characterization, as I said, is not so standard. I found this article by Bob Kraut and Paul Resnick, central people in the CSCW community, and they characterize it quite nicely without creating the term as such. So they focus on the production, and there is the direct production activity, but there is also the coordination activity. And both are important if you want to understand how these communities function. Okay, now we come to the analysis of these POCs, productive online communities, and we have heard that there was a recent project, a European project called CS-Track, which dealt with citizen science as an activity context. We usually, or in some of our analyses, we used the project forums of these citizen science projects as a data source. We have been looking at a number of so-called Zooniverse projects. Zooniverse is a platform that has several such projects. Particularly, we have, our first example was a project called Chimpanzee that collects video data from webcams in the rainforest in Central Africa. So you may detect animals, particularly chimpanzees, and the volunteers, the citizen scientists, they take these data, they don't collect the data, but they analyze these videos and annotate them. That's their contribution. Okay, there are, if you look at the forums, there are assigned roles in these forums. You have moderators, you have scientists more in the background usually, and then you have the volunteers coming in. Volunteers are many, moderators and scientists are a few. And here, what you see here in the first diagram is the development of, yes, in this case, I used eigenvector centrality. Anyway, I used eigenvector centrality to characterize their activity level over time. You see moderators going down a bit, scientists staying on a lower level, and volunteers growing. This is per individual volunteer. Of course, there are many volunteers. Yeah? So then we have also looked at the discourse patterns in these forum dialogues. And the forums are structured. They have different boards. Here we have looked at the help board, the chat board, the science board. And here you see for the different roles that we find in the attributes of the users. This is all open. These data are intentionally kept open, so you can just read that from the forums. And you see, for instance, here, moderators, volunteers, quite active on the help board. You might say, oh, that's the same, more or less the same connection between request help and initiating or giving help that is strong for volunteers on moderators. Now we come to a limitation of standard ENA. You don't see the directionality here. You may suppose behind, when you see these data, that the help giving comes more from the moderators and the help seeking more from the volunteers. But they co-occur in both cases, which gives a similar appearance in terms of this line. What you also see is that the scientists are not so much directly involved, but they come in when things are being discussed. So you can say the scientists usually come in later. The first steps happen between the volunteers and the moderators. Again, this was work together with Ishari Amarasinghe, first author, in work that we can already consider postdoc work for her, because her PhD was in the first context. Now, if we look at our community, and I just took a smaller time window over the Greenwich conferences here from 2011 to 2014, we find quite frequent contributions from this area, particularly related to open source software development. So more specifically, open source software development. For instance, here, when we had the conference in 2012 in Germany, there were 2 papers. There was a 2011 paper, and also then we have a 2014 paper. I think it's no longer that prominent as a topic in our community, but all these people are still active, unfortunately. These were all from Brazil. Unfortunately, we have left them. They are no longer part of our community, but they have made very interesting contributions. I'm going to walk you through a bit of this. That was the 2012 paper by Oliva and Marco Gerosa. Some of you will remember him as an active member of our community. The object of study was the Apache Ant project, and the goal was to identify and characterize key developers in these projects, so the core people in this project. In their modeling approach, network modeling approach, they looked at various types and layers of networks. There was the productive activity in the coding. How can you turn that into a network? People contributing to the same module, code module in the versioning system would be connected. Yeah? And also then you can count the frequency, so you can give edge weights to the dependencies. There is additionally, for the code base, there is a logical structure of the code base, which is a hierarchical graph, so also a type of network that you can use. And of course, there is the communication. Communication in all these open source activities is open. You can read the emails, yeah, by definition and intentionally. So they have analyzed that, and they have used that to characterize the key developers. Just to remind you of what Kraut and Resnick said here, we see this duality, the direct production work and the coordination work. Both is considered here in terms of networks. Second example from our work in 2013, we have compared 3 different open source software developer communities, among them OpenSim that we were talking about yesterday, so the open version of Second Life. We have also used several community detection algorithms. So algorithms that structure the community into subgroups that interact more densely, more closely, and also allow you to look at their interconnections. When I say look at their interconnections, it's very important if the community detection method gives you overlaps. And now you need to be careful. You have all the libraries out there. Some of the community detection methods make what is called partitions. There are by definition no overlaps. So if you want overlaps, you need to choose the adequate approaches. We have used here 2 approaches with overlaps and 1 that did not give overlaps. And we have looked at the network dynamics over time. This is first some general data about the network dynamics, that you see here. I want to draw your attention to this, say the first example, asterisk. You see it's characterized by a decreasing number of nodes, of active participants over time, and density is going up. I would say, oh, less people, but they are working more closely together. Be very careful. The density measure has a characteristic that in an evolving network, the density will decrease. It's a mathematical property of a so-called scale-free network, and most of our networks develop in a scale-free way, that the density will decrease over time when the network grows. What will not decrease over time is the average degree, like your supposedly 300 Facebook friends. That will be quite stable, but if the network grows, Facebook we have seen several powers of 10 in the development. Although the average degree, or if the average degree remains more or less stable, it means that the density will decrease anti-proportional to n, to the number of users. So this can be very deceiving if you look at density. Just wanted to show you this here. What we have also been looking at on an even more sophisticated level, in the comparison between these methods that allow detection of overlaps or not, we have looked at, because we look at time series of networks here, the evolution, the question is the window size of the sampling of the network. So you can use a day. A day is usually not good because not enough significant things happen during one day. A week, a month, and we had several measures, quality measures, like the maximum number of clusters that you detect based on a certain sampling size, or the average number of clusters. The standard deviation of this number gives you in how far it detects differences. You want to detect differences. And you see here in the first period, that was for, I think it was for the OpenSIM network. In the first period, there are not too many subgroups identified at all. But in the second period, days 120 to 540, you see this goes over years. You see that there is a sweet spot in around, don't like me, these devices. You see here, there is a sweet spot where you have differences and you have a higher number of clusters that are identified, and this is around 60 days or 60, 80 days. So we were looking for a sweet spot for the sampling, and here we found it in that area. All these are important questions when you apply these approaches. And that's my last example for open source software development community analytics by Mohsen Shahriari, Ralf Klammer, and Martin Jarke from Aachen University. Last year, we commemorated Ralf Klammer. He has made so many important contributions to our field. Unfortunately, also his former head of institute, Martin Jarke, he also died meanwhile. So let's think of them as having made very important contributions to our field. Here, it is a game theoretic approach. This is based on a game theoretic approach to defining cooperativity. So cooperativity is the target concept, and in this game theoretic approach, they contrast cooperativity to defection. So active cooperation versus leaving or no longer participating. With an underlying game theoretic model. They also use different algorithms, or could also say implementations for detecting overlapping communities. The types of algorithms are not so clearly explained here. They had a huge database with data sets from 70 open source software development projects, and they contrasted them. Now this brings us back to the learning area, to 48 examples of learning forum networks. And what you see here is that when you look at the correlations of community network measures with the target variable of cooperativity, you see very different profiles. This is for OSSD, I should say, open source software creation or development, so it should be D. And you should also see the average def should be average degree. You see that these dependencies or interrelations, contingencies between network measures and the target of cooperativity are quite different. Where does that come from? The variation here lies only in the methods, which means the methods really create different subdivisions. That's not such a nice story for us as users of network analysis, but you get quite different results if you use different techniques, and you need to be aware of that. What they do here in this approach, they just use what they have as a basis for training a classifier to predict cooperativity, which works well. But for a deeper understanding, of course, this is not so helpful. So what they did makes sense, but of course it leaves us also with a challenge that we really have to understand well what the different profiles are and where they come from, and what this means for the methods that we choose. Okay, let's my last example related to CSCW and particularly POX. And here is my look back to network analysis techniques in general. So we have been talking about centrality measures. Reciprocity is not much negative to say about. It's an easy concept, needs directed graphs, and then you can just calculate for all the pairs of nodes that have interconnections, how many of them have bidirectional interconnections. That's the basic measure. Can be very nicely interpreted in terms of cooperativity. Here, density and average degree. I hope you got that message. Be careful. Average degree tends to be more stable in evolving networks. If you use density and the network size is changing, growing or shrinking, be really careful. Density is a deceiving concept there, and that's mathematically grounded. So there is a concept that I have not yet mentioned. This is called positional analysis, connected to a technique called block modeling. This is a technique that allows you to detect not subcommunities. It's often confounded with that, but that's not the point here. It's identifying groups of nodes in a network that have similar patterns of relations to the rest of the network. My standard example, for instance, in the lecture always was, think of a university or research institute and there are secretaries. The secretaries will have very similar relation patterns to a head of department or whatever, to their boss. They are not necessarily densely connected among themselves. Depends on the policy if you want your secretaries to have coffee together every day or so. But that they have different relational patterns to others, that's very distinguishing. So this is what positional analysis gives you. We will see an example in the last part. I have made the plea for using multipartite graphs. Be careful if you use structural measures, for instance, to do with triangle structures. In a bipartite graph, you cannot have triangles. If you have nodes of type A and B, you cannot make up a triangle A, B, A, and A again, because A and A is forbidden. So you need to replace triangles by squares. Same for clustering coefficient. So be careful, you need to look for different implementations, but usually it's worthwhile doing so because it's information richer. And then we have the points about dynamic evolutionary methods. A single network does not contain time. So if you want to look at time, you need time series of networks. And then what we have seen is the window sampling, the sampling window issue. Other issues are, for instance, to do with visualization. Often, a small change in a network structure can make a rearrangement of the automatic rendering algorithm so that it's not easy to identify where the same nodes are in the next time slice. We had a PhD project also on that, but here I can only mention it. Okay, that was the second part, and I think 15 minutes more is okay, right? Because we started a bit later. That should suffice. Now to recent developments involving new AI. First, a little reflection on where we are without repeating the standard things about generative AI, etc. So in general, if we look at that, the shift from classical AI to new AI, the interesting thing is that new AI with deep learning does do away, to a certain extent, with the need for complex knowledge engineering to start with. If you use real deep learning, you can even omit feature engineering that we know from many statistical approaches also completely. You have efficient processing, that's the good thing. You can handle large data volumes. This is even supported by special hardware, the GPUs, you have libraries, it's all at hand, it's all there. What are the problems? These approaches are based on numerical representations, so-called vector embeddings, and it's not easy to read or interpret such vector embeddings. So there is an inherent intransparency here. We call it the black box property of these models, and that has been much discussed. And it led to the discussion about adding on explanation and explainability techniques. That's the explainability challenge. If we shift our perspective to what that means to the researchers and to the research work, the question is, if we work with such approaches, how far does the data model, the representation that we use, support us in finding research questions, hypotheses, give interpretations of the data? If we consider what we have seen with the networks, NTA, ENA, standard social network analysis, they are suggestive. You can read the networks as a human, yeah? Whereas with deep ML, deep machine learning, and new AI approaches, we operate on these vector embeddings, which are not so clearly interpretable. So what we hope is that in the vector space, we can define measures that will allow us to regenerate the same kind of dependencies and properties as measures in the vector space, the ones that we have used before in the structural models. This is, I find, a very nice illustration of the point made by several people. It was a survey article in the field of computational biology, but you don't have to enter into computational biology here to understand that. The point is that we have the network representations here, and they are transformed. They are transformed into the vectors, converted into the vector space as clouds of points, data points in the vector space, like here and here. Here, for instance, you may have been interested in the subcommunity structure, quite evident. And hopefully, in the vector space, you get that also. You could find clusters in the vector space that would correspond to the structural components here. And then you can look at different, here, this is for community detection. It's this example. You could look at alignments or predict certain functions, like in computational biology. This is very important. One of the important authors of this paper is Jure Leskovec. If you have searched for him, he has a huge, incredibly huge H index, and all these papers are cited so many times. And this Jure Leskovec, together with, first name I don't remember, Grover, he invented a technique called node-to-vec, and this technique exactly does the vector embeddings. And this is what they claim in the initial paper about this approach. They claim that their vector embeddings of graphs allow for, depending on the parameterization that you use, allow for addressing and detecting structural equivalence. This is the positional modeling, the similar relations. Also homophily, you may have heard homophily means. The homophily claim is that if you have attributed nodes with properties, that nodes with similar properties will have a higher likelihood of being connected in the network to nodes that are not so similar in their attributes. Yeah. So, and he claims, or they claim, that this can be detected from the networks. And this is based on a random walk approach, but I will not go into the details here. So when we go to particularly focus on the structural similarity and equivalence, you see here, in this small network, there are nodes C, D, and E. They have a quite high degree. They are connected to both sides, to put it this way. A and B even have the same connections, literally the same connections to all nodes C, D, and E. So they have same links, but here, from the perspective of C, D, and E, vice versa, they have not the same connections. For instance, E does not have a connection to F. But if you say F and G are one class, you can say they interconnect between the same classes of nodes. This is what we call regular equivalence. So this is what we are looking at. And how can that be interesting? Remember the secretaries example that I gave. This is about roles. This is about role modeling. And roles are very important to us for the analysis of collaboration, particularly in non-homogeneous teams. So we had earlier work in the context of MOOC studies where we used role modeling in MOOC discussion forums. And of course, the idea is always how do you connect that to learning? We used the ICAP model, come back to that in the next slide, and several other indicators to identify roles and role changes in this context. And here the main point was about help giving, help taking as a main indicator of roles. Okay, the ICAP model or the ICAP framework helps us to characterize different levels of engagement of users, in this case in a learning community. So what is called interactive by Chi and Wiley, we would usually call it cooperative, but they called it interactive. So it reads ICAP from when you read it from top to bottom. That's why it is called the ICAP model. And we want to use that as characterization of cognitive engagement. This is what it is originally defined as, and an indicator of learning. If you look at the paper by Ahmad and others, they give a survey on such applications if you're interested in that. So our application is again the citizen science context. You can think of the chimpanzee forum on Zooniverse. We have the forum posts. We create networks from the forum posts. This has been done in an earlier paper already that was presented at Collabtech 2022. Now we have used vector embeddings. Now we have added, and this comes from ongoing work by Simon Krukowski, Ph.D. student of mine. So he has used Node2Vec to embed the networks that we had previously generated into a vector space. And what you see here, interestingly, is that, we have the declared roles. This is not roles that we had to detect, but you can find them. Somebody is assigned as a moderator, assigned as a team, assigned as a volunteer. Team is not so important here. Look particularly at moderators and volunteers. Interestingly, in the vector space, the moderators form a cloud, and the volunteers. Oh, yeah. Oops. And the volunteers also form a cloud. This is good news, because there should be similarities, and we see the similarities. Thank you. So we can also see that the volunteer cloud is quite widespread. Of course, volunteers are not all equal. We know from the analysis of online communities that you have very different levels of active participation. So this is no surprise. But the good thing is, yes, we can distinguish them. Okay. And there, now we should have a video. Maybe I try to do it. Yeah. So we see these network clusters. And here is a bit of, this is a dashboard that Simon has created that allows us to interactively browse on a timeline through the data, and then at a point in time, we can look at different projections of the data. So you see, depending on the perspective that you take, this distinction of the clusters is more or less clearly visible. So the 2D projections can be deceiving, but it's clear. they are projections from much higher space. Even if you are on 3D, the real projection is from a much higher dimensional data space than what we see here anyway. Okay. So, and in our most recent work here, we have, that was presented at the AIAD conference this year, we have been looking more deeply into these data and particularly compared there were, now it's an interesting thing that some of the volunteers are, during the course of the project work, they are promoted to moderators. And we have been looking at the profile of these users that were promoted to moderators, particularly before the promotion. You can say once they are promoted, they have to fulfill the role model of moderators anyway, so that would not be a surprise. But how do they develop before promotion? So you see here, this is in the diagram, this is months until promotion. And we have looked at differences in the vector space. And you see the differences in the vector space, this reddish color, it goes down. And we had another variable that is what we call the degree ratio between in and out degree, a directed network. And you see this degree ratio goes up, and we found the degree ratio also being a good indicator for taking over moderator roles. Okay, so you see, it appears to work, but still the question remains for us as researchers, now that we have the new models with vector embeddings, what does it mean for our inspiration? I mean, the benefits are clear. You have one representation, very flexible. You can turn it around also by parameterization, even supporting different types of network interpretations. But if I imagine we have a future generation of young researchers who from the beginning work with these vector embeddings, what is their understanding of the network properties? So my consequence is that lectures like this one are still needed, even though we may use vector embeddings. But that's now up to you to raise further questions or comments. Thank you very much for your attention.
Thank you very much for this comprehensive and inspiring presentation. And now there is time for comments and questions by the audience. We have already a question there by Khadija. Okay.
All right, good morning. First of all, thank you for this really, really wonderful presentation. I myself am a student that is exploring the world of network analysis, and I had the chance to apply it in one of my last works. It's still in review, so I hope it gets accepted. My question is about the kind of data that, for example, I work with is kind of sensitive, let's say, because it's psychological factors, including, for example, emotions, behaviors, and personal inclinations. So I had this question about, I do believe social networks are to make complex data easier to understand, but how can I avoid to fall into simplicity or even like watering down the interpretation of the results? Thank you.
Thanks for the question. Let me ask you the one or the other clarifying question. Are you using network embedding also, or just plain network analysis?
Just plain network analysis.
But as far as I understood, you have attributes.
Yes.
So you have attributes. What you can then do is, you can look at the network structure, and then I mentioned this homophily assumption. You would usually expect that the network structure, in a way, reflects the attribute similarities, which is not always the case. For instance, if there are properties like you live in a certain area, then of course it's much more likely that you are connected to people who live in the same area. or age is, if you go to certain clubs or not, age is an important thing. But in a family belonging does not depend on age. Yeah, so we belong to a family over our lifetime. So it's very interesting to look at these interrelations between the attributes and the network structures and identify the attributes that, say, are congruent with the network structure and identify the attributes that are more or less independent of the network structure. So that would mean that you would typically use clustering techniques based on the attributes in comparison to network structuring techniques. And this is, of course, very general, but we would have to look a bit more into your data. You mentioned, say, privacy, anonymization. Of course, you can use, for instance, here, with the data that we have taken from the, say, open data sources on the web, even there, you should be careful. I mean, if there are real names used in the forums, the question is if you really reproduce them. You would usually not. You can use pseudonyms to avoid that. But sometimes if the usernames are already coded in a way, then this is not so much of a problem. Also, if you aggregate the data, this usually does away with the anonymization challenge. So I don't know if I've touched on some of your questions or...
The first part, it was, you did address it, but the second one was about not so much the anonymization of data itself, but for example, psychological factors. We should be more careful when interpreting these things because it involves health of the individual.
Yeah.
So that was my question about how can we look at it from different perspectives instead of only interpreting the network analysis itself. How can I accompany it with, let's say, empirical other methods, for example.
Yeah, I mean, this comes back to the first part. So if you have psychological properties, for instance, you look at, very early example, the sociograms, say the social structure in a group, in how far is the structure strongly influenced by certain, for instance, personality traits, or in how far is it not, depending on the personality characteristics. Yeah. So, thank you.
More questions or comments about the audience? I'm interested in knowing general thoughts about your experience working interdisciplinarily and the relevance that it has to apply the analytics. So you said at the beginning that network analysis and social network analysis is an interdisciplinary project. You have been involved in interdisciplinary project and has been collaborating with people from different disciplines. So I would like to know what is your experience, what is your recommendation when working interdisciplinary projects, and how relevant is this interdisciplinary understanding of problems when it comes to choose sampling windows and other elements that you explained in your presentation today.
Yeah, I would say that using networks as representations can even mediate between disciplines, because network analysis techniques are used in many different disciplines, and you find people, say, there is much more commonality across disciplines with network analysis techniques than, say, with sophisticated programming techniques. Yeah, that's more biased towards the computer scientists. In sociology, there is this notion of boundary objects. Boundary objects can help you to communicate by using the objects as mediating your discussion, discourse. And I would even say network representations can be boundary objects, so they are helpful. I would not just, of course, from both sides or from all the sides, you need a certain willingness and also familiarity, but how you understand the networks and in how far you are familiar with the techniques behind, that can vary. Still, the network representations and also certain methods that you know basically what they do, they can help to understand each other better. So I would see it positively, yeah.
I agree. More comments or questions? We have one by Joaquin. Matthias, yeah, Joaquin, I saw you late. Sorry, Matthias.
Thank you. Very, very good class. This is a master class. Very, very nice. I have a question with the ENA when you classify the interaction. How do you classify the interaction? Manually, or are you using artificial intelligence to classify?
Good question. The early ENA work was often based on human coding to identify these basic codes. They're talking about the codes. But they also have now machine learning supported techniques. You and your group have used encoder quite a lot, Davinia, right? This is such a technique that feeds into ENA. So yes, as one would expect, this exists now, but much of the earlier work was based on human coding, which is of course an issue because it means you can only use it ex post. Yeah, so you need some time in between. Yeah, thank you.
Thank you for interesting talk. So my question is about the value of the network analysis. So I understand basically being able to understand by graph, so is a value of the network analysis. On the other hand, in case of the design area, service design area, the method called the causal loop is for finding leverage point for a solution. So it's a value is being able to design. Mm-hmm. So I'd like to know your opinion about the value or potential of network analysis. So the understanding, designing, or any other one. How do you think about it?
Certainly in first place from an analytical perspective. So if it comes to design, generating solutions, I would not claim this to be a strength of network analysis as such. It's deeper understanding, in terms of the structural relations that you have. There are, even on that level, there are misconceptions. People often say, we identify interaction patterns in networks. Networks have no time. A single network has no time. If you want time, it's more complicated. So there are also misunderstandings. Also, just to support your question rather than giving an answer, what we found with our CSCL data was exactly that papers on design, CSCL design, were not so much related to network analysis, which is simply true. So I would not claim that network analysis is the solution to everything. But so I would rather turn your question in the following way, that you say that we should develop, and I haven't done that today, and it's a difficult challenge, to define how network analysis can complement other techniques, say more, and I would say more design-oriented techniques. How can it feed into that so that we have an overall methodology in which network analysis plays a role, but also, say, more design-oriented generative technique. Speaking of AI, this is not generative AI. Also in the network embeddings, that's analytic AI. Yeah, it's not generative AI. So that's another very interesting challenge, and I would not claim that network analysis as such is the solution for your important point.
Thank you very much.
Thank you for the question.
With this question, we close the session. Again, it was a pleasure listening to this very comprehensive masterclass presentation. I'm glad we recorded it, and this will be, and other people will be able to enjoy and learn from the presentation in the future. Thank you very much to all. Thank you very much to the keynote speaker, to Ulrich.
Thank you very much for your characterization of this as a masterclass. Because if I miss something after my retirement, that's that. I mean, not only this class, but also this class that I gave. Was really a part of my academic life that I miss now in this new phase. Thank you.
And now, this is for you, small gift. Again, remember yesterday, the Castellers, really a collaborative endeavor, a Catalan tradition, and these are Catalan biscuits in a nice box for Ulrich. And also for him, remember we are at Pompeu Fabra University. We are hosting the conference, and this is a t-shirt from our university and the engineering school for you.
Thank you very much again, Davinia, for inviting me. To Patricia also.
Let's do a picture.